Back in Chapter 2, we studied the dynamics of single mass systems. We looked at the dynamics both in the homogeneous case, where we had an initial position or potentially initial velocity but no external forcing, and then again in the non-homogeneous case, where we added a time-varying external forcing term with a frequency that could be tuned until resonance occurs. Even more interesting dynamics start to arise when we consider two carts connected in our system. We can displace these carts in many different ways, for example, in the same direction. If the cars are displaced in the same direction, notice how their motions roughly mimic each other throughout the rest of the experiment. However, I can also displace them in opposing directions, in which case their motion is oppositional and they butt heads throughout their time. A third option is that I can hold one of them steady and displace the second car, which results in this definitely more erratic kind of motion that you see one car going back and forth and etc. until I eventually stop them from their motion. We can also play the game of adding an external forcing to our system. We can start to increase the frequency of oscillations and see how this now affects the motion of our cars. As with the one-car system, a very low input frequency does very little to affect the motion of the cars, and they stay roughly stationary. As I increase the motion of my input frequency, notice how the cars start to move together faster and faster until we hit what we could call again a resonant frequency, where the cars are moving very quickly together in the same direction. Now, interestingly, if I start to speed up the frequency past this resonant frequency, stop the cars and do this experiment again, the cars start to exhibit some kind of oppositional motion. And at first that motion is small, but as I increase it, the amplitude of their oscillations increases until they eventually crash into each other. If we reset our system again and try and have our input oscillate at an even faster frequency, we will no longer see this kind of crazy behavior. We'll start to see the motion of the cars slow down again, as we did in the one-cart case. The two-car system, therefore, leads to one of the most interesting frequency response plots we've seen thus far. If we create a plot where frequency of input is on the x-axis, and the amplitude of car 1, for example, is on the y, what we'll see is this sort of two-hump function, where there will now be two sweet spots frequencies, and there'll be a decay as the frequency of the input goes towards infinity or towards 0. The goal of this next part of Module 3 is going to be to model this two-car system and explain these phenomena by looking at the eigenvalues of a corresponding coefficient matrix.